not an issue.
All right, so are you ready to get started?
Yeah, I would suggest we go on.
Awesome, okay. Our next talk is from Barbara Osimani, who's joining us from the Faculty of Medicine, the Polytechnic University of Marche at Ancona. Her talk is titled The Causal Structure of Epistemic Environments. So Barbara, take it away.
Thank you, Maria. So I have to do this, okay. So we gave a talk in two parts, given this mixed audience of scientists and philosophers to show scientists how philosophers can be really relevant to the discipline, not only, let's say, from a philosophical point of view, ethical point of view, but also formal philosophy can sometimes help in identifying dimensions in scientific inference that can be maybe helpful also in daily business with methodological issues. So the first part, we present the ERC project, which just finished. So I want to present the people, but also the motivation that pushed me to work on it. And then also the results of our collaboration with the agencies across Europe. This is very interesting because let's say, the epistemic framework that we developed from philosophical foundations is now seeming helpful also with the work with drug agencies, especially the Italian one, the Austrian one, and the French one. We are also doing papers together with them on specific case studies in order to develop our framework. And the project was also philosophical, so we did also philosophical work on evidence and inference in medicine. What I will present in the second part is exactly this philosophical, more formal work. And I would really appreciate also feedback from scientists in the sense of seeing whether this helped them in some way to think differently about evidence. Okay, do this. So the motivation was the complexity of scientific inference in the medical environment. We can see it now, for instance, in the COVID case. There are a lot of dimensions intertwined. First of all, medical products are so-called credence goods, that is, products for which the consumer medical community, patients, and public health system, in a more general sense, cannot evaluate the quality prior and often not even after consumption. So there is a structural information asymmetry between the different providers of knowledge from the pharmaceutical industry or the university research industry, let's say, to the health system, and then the doctors and the patient. And this also for the quality of the evidence provided by producers of knowledge in this field. We saw in this COVID case how many papers were put out, but it was very difficult to analyze to evaluate their quality. On the other side, we needed some data in order to make decisions. So we have to evaluate evidence as a vector of different dimensions. And medical decisions are intertwined with pressing ethical dilemmas, where the good at stake can be the same for all alternative actions. Health, you can have benefits and harms from the same technology. And medical decisions are characterized by high stakes, both in terms of physical, psychological, existential, and financial costs, both at an individual and collective level. Finally, producers of medical knowledge often have vested interests in the research outputs and dissemination, leading them to engage in strategic behavior, which obviously exploits all of the above. So there are institutional instruments to counteract this exploitation of uncertainty from the knowledge producers to the knowledge consumers with this epistemic asymmetry. One, of course, is the most important, is the evidential standards, such as the evidence hierarchies proposed within the ABM paradigm. But sometimes these evidential standards become obsolete because it's exactly by sticking to them that industry can evade the very purpose for which they were developed. The ontological norms and instruments of sanctions, such as reproducibility requirements and bias detection tools, for instance, trial registries or ex post meta-science studies, which detect whether the study was in a pool of studies where there was bias or, let's say, evidence distortion in some way. And then decision rules, such as the precautionary principle. Sometimes there is also some misunderstanding in this kind of norms or principles. We see it, sometimes they are even exploited for strategic purposes. So scientists are advocating and have advocated for a more comprehensive view of evidence, which may incorporate these issues explicitly and keep track of them in the inferential process. Andrew Gellman, the famous statistician, but also other statisticians. And also now there is a game theoretic interest, the interest of game theorists in these, in the epistemic asymmetries in science. For instance, there is a wonderful work by Ottaviani, but Bayesian, the discipline of Bayesian persuasion is very, very interested in this kind of work, and we are also interested in it. So our project started with by looking at the state of the art in the regulatory context. The European Parliament and the European Council have changed the regulation of pharmacovigilance practice, and the related guidelines encourage the integration of information coming from different sources of safety signals. Yet the methodological basis for implementing such a policy are shaky. I could say they were shaky because now we developed, after 5 years of project, the basis for such a methodological shift. And as there are these asymmetries between evaluating benefit and harm that were not so very clear at the beginning of the project, and now we really push them through in the different agencies. So the evaluation of intended beneficial effects of interventions may rely on experimental studies. Instead, you cannot experiment for harm, and data pooling, meta-analysis, and systematic reviews of homogeneous studies. Risk detection generally and discovery is characterized by relative scarcity, heterogeneity, and fragility of data. And this concerns, of course, the safety of technology. Okay. So the causal assessment of adverse drug reactions is parasitic on the statistical methods developed to test drug efficacy. At least I might say in the sense of a forma mentis that the people have with regard to evidence. They still stick with maximizing internal validity and accuracy to the, let's say, by neglecting aspects that cannot be neglected in the assessment of safety. So this kind of methods developed for assessing benefits are focused on hypothesis testing rather than discovery and hypothesis generation. So they fall short of using sporadic, fragile, and heterogeneous evidence efficiently, and considers the strategic distortion of evidence in an ad hoc fashion. And the project PhilPharm, Philosophy of Pharmacology, Safety, Statistical Standards, and Evidence Amalgamation, has addressed this problem by developing a theoretical framework for the justification of probabilistic confirmation of causal hypothesis on the basis of all available evidence on safety for medical treatments. The framework is synthesis. Now, the point is that what we see in the clinical trials or in general frequency statistics is a dichotomous approach. You accept or reject the hypothesis. We wanted something more flexible. You update continuously on the probability that there is a causal link between the drug and the side effect. So these are the people that are worked and are still working with me, some of them. So Jürgen Landes is still at MCMP LMU. He's a former philosopher. You might know him. He's a very, very good mathematician. He was very excited about this project from the beginning. I'm very happy that he's keeping on also with another project funded by the DFK. Roland Pollinger also helped with developing the synthesis framework. He's now out of the academy because he wanted a fast job, so study job. Todd Stamberg is no longer in the project. He's in New York and he's a game theoretician. Mantas is a game theoretician and he's in the project still. We are working at game theoretic approaches to reproducibility crisis, these kind of things. Francesco De Pretis is a mathematician. He works at Ancona, the project. He's in a tenure track. Armando Sacco is a game theoretician. He's now in a tenure track in Naples. Stefano Bonzi is a mathematician. He's now in Turin with Jan Sprenger. And Maria Laurelardo is a newcomer. She's my PhD student. She's also very interested in these topics. So these are some of the papers that we published recently. One of Frontiers, we are very proud of it. And this was the foundational philosophical paper that we wrote, Epistemology of Causal Inference in Pharmacology towards a framework for the assessment of harms. I briefly present it and then I go on with the more formal part. So we had this idea to use Bayesian nets, especially epistemic nets, especially coming from above the heart, the Bayesian epistemology tradition. and updating them in some sense. So we have here not a generic hypothesis. I mean, this could be any scientific hypothesis with its own consequences, which are more probable than not to be observed if the hypothesis is true. And then, can you see also my arrow coming up and down? Oh, perfect. And then you can see a report, which is a consequence of the consequence of the consequence of the hypothesis, in the sense that if the observable consequence of the hypothesis holds, then you should see more probably than not, I don't know, a statistical report or an observational data that tells you, yes, this is true or this is not true. We have also this reliability node that tells you whether your source of evidence is reliable. I mean, these are binary variables in Bovezet-Hartmann. You can also make them continuous, but this is just to simplify things. So the hypothesis may hold or not. Then the consequence may hold or not if the hypothesis holds with a certain probability. And also the report, you may see or receive a report about the consequence with a certain probability, depending also on the reliability of your source of evidence. Now, for us, the hypothesis is a causal hypothesis. It is, for instance, paracetamol causes asthma in a certain model at a certain population. What does this mean? That, of course, causal hypotheses in medicine are not like in physics. You may have that a drug works in a certain group of patients and not in a certain other group of patients, depending on the causal structure in which the molecule of the drug becomes to be embedded at the biological level, but also at the sociological level in the sense of cofactors like age or I don't know, gender, whatever, sex, or whatever. Okay, so our idea is that we have this causal hypothesis up here, which is the antecedent of different possible consequences in the sense of indicators of causation. The main indicators of causation is difference making, which is an asymmetric relation between the putative cause and the effect. If you, by intervening, you see that by intervening on the cause, something happens to the effect, then you have very valuable evidence that indeed this was the cause and the other, the effect. And if you intervene on the effect, you will see nothing because by intervening, you make the cause and effect independent. And so we consider difference making as one of the most important indicators of causation. And this explains why then evidence that inform us about difference making, such as randomized clinical trials, is privileged in evidence-based hierarchies, in evidence hierarchies. So the point is that it is because difference making is such an important indicator of causation that for instance, a report like a randomized clinical trial that can give you information about difference making is so important in medicine. Instead, other kind of indicators such as probabilistic dependence or dose response or rate of growth, they're also indicators of causation, but they're not conclusive ones. So reports about them, which can come from observational studies like in epidemiology, probabilistic dependence can come, for instance, from a cohort study, either prospective or retrospective. Dose response also, but it needs to have more arms, or more exposures levels. Rate of growth, the same. And rate of growth tells you how much there is this steepness in the dose response curve. These are also abstract indicators of causation, which update on the probability that there is a causal connection between the drug and the side effect. But they are fed in by different kinds of reports, observational studies. For each report, you can see this reliability node that tells you how much you think that the source is reliable in the sense of internal validity, for instance, or external validity. We'll come back there. Then there is the node of mechanism. You might have for instance, evidence about the pharmacokinetics of the drug. It is interesting to know now, for instance, with the COVID-19 case, that there is a lot of, let's say, strong mechanistic evidence about the functioning of hydroxychloroquine at the molecular level, because they inhibit the virus and so on and so forth. But then at the phenotypic level, when you look at randomized control trials, I mean here, or at epidemiological studies, You don't see any significant difference. It would be interesting to explain this conflict of evidence. Time, this is the indicator. I mean, of course, in biology, we're not speaking about quantum physics or things like that. In biology, causes precede their effect. So if you evidence that there is time precedence between the cause and the effect, this is also an indicator of causation, and so on and so forth. When we brought this framework to the drug agencies, it was interesting to see how they reacted. For instance, the French, responsible for pharmacovigilance of the French agency told us, this is how I think. It was interesting. I mean, I was really happy. I mean, it seems very abstract, but indeed it represents a little bit the kind of reasoning that you have in this context. Of course, not for every case. That's why we are trying now to implement this in concrete cases and see the limits and the rooms for improvement. For instance, a room of improvement is that we expanded out the reliability and relevance nodes into the random error node, which is represented by samples, sample size and duration of the study. The larger the sample size, the less random error, and also the larger the duration of the study, the less random error. And systematic error, which can be, let's say, expanded in adjustment, sponsorship bias, and then, sorry, I can see there's the sponsorship bias, blinding, and randomization. Sorry. Okay. So let's go to the formal framework that I wanted to present you. I will present it by introducing 3 toy examples just to stimulate your imagination, and then see what your imagination tells you with respect to our results, whether it matches in some way or not. So 3 toy examples. Okay. So we have 2 consistent studies in PubMed. Suppose you are a general doctor who needs to prescribe a therapy for a patient with an uncommon disease that you can pretty well diagnose, about whose most cutting-edge treatments you are, however, unaware. So you're not very expert. You're a doctor, but you're not an expert. You make a quick search on PubMed and find out that a new treatment has recently been tested for this specific condition in 2 distinct studies. Since this is not your specialty, you do not know the people who do the research in this area, how good they are at making research, or how biased they may be because of possible vested interests. Suppose the studies are of equal quality at face value, that is, they have the same capacity to detect true positives and false positives. Would the 2 studies be more confirmatory for you with respect to the hypothesis of efficacy if they came from the same research group, or if they came from 2 completely independent ones? Now, the other 2 toy examples are the same. They are analogous, but just 2 different contexts. 2 convergent forensics. Consider a court jury involved in judging a culprit for having committed a crime. They receive 2 forensics regarding the same type of evidence. For instance, hair material or blood or traces of genetic material, delivering some confirmatory support to the hypothesis of guilt. Would these forensics be more confirmatory if they came from distant labs or from the same one? Then, to evaluate studies on fiscal policy interventions, a governmental body needs to make policy decisions regarding the 5 next years of fiscal regulations. Before involving expert groups, they consult scientific databases and search for empirical data regarding various fiscal interventions in diverse countries, looking for evidence as close as possible to the historical and political situation they are dealing with. They find 2 relevant studies, which investigated the efficacy of a given fiscal program and delivered evidence at the same significance level and power. Would they find the fiscal scheme more or less efficacious if the 2 studies came from the same source or from different sources of information? Okay, it depends. But what is interesting is what it depends on. The things the answer depends upon are revealing of various essential forces in statistical inference, namely random and systematic error, which in turn depend on nature and sender. The interaction of these diverse forces has not yet received explicit attention. So the game theoretic part of people in my project are dealing with these strategic aspects. Here I'm focusing on random and systematic error. The main intuition behind all this is that many aspects implicitly or explicitly factor in when we assess evidence. And this is another paper which is forthcoming, hopefully soon. It has been there for years. Okay, varied evidence. So, consistent findings from different routes converging to the same hypothesis are more confirmatory than if they came from the same one, since it is easier to explain this coincidence if the investigated hypothesis is true rather than not. If the hypothesis were false, one would need an alternative explanation for such coincidence of measurements. For instance, there is an analogy with testimonies in legal evidence. Is it a coincidence of the two testimonies saying the same thing, or is there collusion between the two testimonies, or there is a common cause, which is truth? The variety of evidence thesis states that items of evidence from independent lines of investigation are more confirmatory, ceteris paribus, than replications of analogous studies coming from the same source. This is a famous statement by Pml. Any working scientist is more impressed with 2 replications in each of 6 highly dissimilar experimental contexts than he is with 12 replications of the same experiment. Indeed, there is an obvious marginal diminishing value in the epistemic gain provided by exact replications. However, there is also common sense intuition for the reasoning that the exact replication gives us important, higher order evidence about the reliability of the instrument itself. In statistics, the rationale that distinguishes the 2 approaches is exact replication, excluding chance results, versus conceptual replication, excluding alternative explanations, study of artifact, latent variables, intentional bias. But what are exactly the parameters that determine this trade-off, and where should the curve lie, and why? Sorry, this should be okay. So Bovens and Hartman developed a formal model of replication in order to show the epistemic interactions between evidence coherence and reliability of the sources in hypothesis testing and testimony. Their results mainly rely on dividing the hypothesis space regarding the truth tracking properties of the instrument in perfectly reliable, the 2 extremes. The instrument is either perfectly reliable with a given probability. I assume that the instrument is perfectly reliable with probability 0.8 or 0.9. And the probability is given by rho is the probability that I assume the instrument to be reliable. Complete randomizer, in this case, the instrument is completely disconnected from reality, can say yes or no, independent of what the truth is. And at the same time, the Bovens and Hartman allowed the rate of positivity reports for the randomizing instrument, A, to vary between 0 and 1. This means that if the instrument is a randomizer, it doesn't mean that it tells yes or no 50% of the time. It can also say yes 90% of the time, but independently of the truth, and say no 10% of the time, independently of the truth. It's a randomizer, but they can vary in the randomizing rate. In the rate with which it has positive or negative responses, but independently of the truth. So here's Bovens Hartman's model, where we took our epistemic framework from. Here we have the hypothesis with a probability attached to it, H. Then there is the probability that the consequence holds if the hypothesis holds, which is P, and the probability that the consequence holds if the hypothesis doesn't hold, which is Q. Now, if we think that we want to observe some consequence of the hypothesis, the probability P should be higher than Q. This is an interesting assumption because the similar frameworks studied by other authors don't have this assumption and then have other results. So we have that. If we assume that we want to test an hypothesis, even in a Popperian sense, I conjecture an implication of the hypothesis, I want to test it. So I assume that I will see, this hypothesis holds more probably, this consequence holds more probably if the hypothesis holds. And then I devise a way to see this consequence. And then I see a report here. And the probability of seeing this report, if the consequence holds, is 1, if the instrument is reliable. Otherwise, if the instrument is not reliable, is still reliable, but the consequence doesn't hold, the probability of seeing the report is 0. So if the instrument is reliable, rel, and the consequence holds, then I have the probability of a report 1. If the instrument is reliable and the consequence doesn't hold, the probability of seeing a report is 0, because it's perfectly reliable. If the instrument is a randomizer, then we have the same probability A of seeing, let's say, the report, given that the consequence holds or doesn't hold, no matter what. So we have A can be 0.9, so we will see a report that the consequence holds with 0.9 probability, whatever the consequence is, whether it's true or not. I hope this is clear. If it's not clear, you can just raise your hand. So for a randomizing instrument, the probability of seeing a report, a positive, is always 0.9. So you have a false positive with probability 9 and a true positive with probability 0.9. Okay, so when we see a report, then the probability, I mean, of course, there is a propagation of probability through Bayes' theorem. So you update both that the hypothesis is true or not, and that the instrument is reliable or not. But when you see more than one report, there are interesting dynamics. There is an interaction between the relationship of the report to the hypothesis and the relationship of the report to the reliability, and there are interactions between the two. So the randomizer can be indeed a real randomizer, a yes man, or a naysayer. In what sense? If you assume that the randomizing instrument has a probability of delivering a positive report with 0.5, then our unreliable instrument is a proper randomizer. However, if A is lower than 0.5, the unreliable instrument tends to be a naysayer. It tends to say no. If A is higher than 0.5, the unreliable instrument tends to be a yes man. It tends to say yes, whatever the truth is. What happens then? So we have, I mean, Bovens-Hartmann studied 3 scenarios. I illustrate to you only the first one. The second one is very particular, and the third one is similar to the first one. And what happens is that they find in another unpublished paper, and also in this paper, this kind of thing, that the too good to be true evidence intuition is violated in their account. They find that the area of that failure in the row A space increases with increasing n. So the more positive reports you receive, the more you prefer to receive them from just one instrument, which is a little bit counterintuitive, because if you receive the same reports from the same instrument, in the end you think, okay, but this is a yes man, I mean, this is unreliable. And so you would prefer to have positive reports but from different instruments which could cross-check each other, let's say. That's why we changed the... So receiving several consistent reports from one single instrument is more confirmatory than receiving them from different ones. And this for an increased number of consistent reports. So it was a little bit strange for them. But this goes against the intuition of too good to be true evidence. So the key to our explanation of Bovens-Hartmann results in the area of that failure grows is the fact that the area of that failure grows in A and not in rho. Let's see how. So you can see here, this is rho and this is A. So this is the probability that the instrument, I mean, the probability that you attach to the instrument being reliable from 0 to 1. And this is the probability with which, if the instrument is unreliable, gives you positive reports. Okay, let's see with 2 reports what happens. If you assume that the instrument is more likely than not, so from 0.5 to 1, the vet holds. So you prefer to receive the 2 reports from 2 distinct sources of evidence instead of just one source of evidence. Let's go back maybe to this thing, because I didn't, yeah, okay, this one. So you can see here, maybe not too much, but so this is the hypothesis, the consequence, and then you see 2 reports either coming from the same source, and this is modeled by having the reliability node being shared by both reports, or the two reports come from two different sources, and this is modeled by the reliability nodes being dependent. Okay. So what happens in these results by Bowens-Hartmann is that, and let me see here, in the first scenario where we have two reports, when you consider the instrument to be more reliable than not, you prefer to have the two reports from the same instrument. And also here, this is the area where the vet holds. This is the area where the vet fails. That is, you prefer to see, it is more confirmatory to receive the two reports from the same instrument. And it is interesting to understand why. The reason is that you consider the instrument to be less reliable than not. So you are more inclined to think that it is a randomizer in your prior. Then, sorry, because, okay. In case you assume that it is a naysayer, because it is less likely than not to give you a positive report, the A probability is from 0 to 0.5, so you may give you, a positive report with probability 0.1, 0.1 or 0.2 or 0.3 or 0.4. So you think that it is a naysayer if it is unreliable. That's why receiving two reports from the same instrument decreases the probability that it is a randomizer, and therefore increases the probability that it is a reliable instrument. That's why it is more boosting to receive these two reports in Bowens-Hartmann from the same instrument rather than from two distinct instruments. Now, why does this space, this area, increases in A? Exactly because even if the instrument tends to say more positive reports than not, but you have, let's see, 10 or 50, and then 2, 4, and then 10, and then infinite, 2, 4, 10, and then infinite reports. If you have infinite reports, you have more space for R to grow until you have this result. Sorry, but okay. So for, I don't know, if you have 10 positive reports from the same instrument, but the probability of having a positive report from the randomizing instrument is up to 0.75, let's say 77, having 10 reports in a row tells you anyway, okay, this is not the randomizer, this is a reliable instrument, because it's more, truth explains these results more than the randomizing instrument. Okay, I hope I'm not too late. Okay. Hence, that failure in Bowens-Hartmann's model is mostly driven by modeling the unreliable source this way. If A is lower than 0.5, the unreliable instrument tends to be a naysayer. And consistency of positive reports from the same instrument boosts the belief in the instrument not being such, and therefore in its being reliable. So there is that failure. Okay. Instead, if you assume that A is higher than 0.5, then our unreliable instrument tends to be a yes man, and consistency of positive reports from the same instrument boosts the belief in it being unreliable indeed, and so you prefer them to come from different instruments. So summary of Bowens-Hartmann results. As a consequence, when the rate of false positives by the randomizing instrument is said to be low, then two positive reports coming from the same instrument decrease the probability that this is a randomizer. Hence, they increase the probability of the complementary hypothesis, it is that the instrument is reliable, thereby boosting the hypothesis confirmation more than they would do if they came from distinct instruments, and that fails. Okay. Now, we wanted to change the model in order to see whether we had something that did not represent this kind of violation of the too good to be true evidence, which comes mainly from the awareness of bias and random error in scientific instruments. Whereas random error averages out through replications, bias exacerbates error throughout replications instead of attenuating it. So we expect that if you have many, many positive reports, you start thinking about bias. So our model is this one. We have the probability of reliability being rho, as in Boas-Huffman. But the probability of positive, the instrument can be also positively biased, and this is P equals 1 minus rho. So our instrument is either reliable or positively biased, but they are not neither of them are deterministic. I mean, neither the reliable instrument is perfectly reliable, nor the biased instrument is deterministic biased. So, for instance, the probability of having a report, if the instrument is reliable and the consequence holds, is 1 minus epsilon, a random error, let's say. And the probability of seeing the report, if the consequence holds and the instrument is positively biased, is alpha, which is a little bit, maybe a little bit or higher than 1 minus epsilon. So it's a little bit more, you have a higher probability of getting a positive report if the instrument is positively biased, higher than if the instrument is reliable but affected by random error. The same for the negative situation where the consequence doesn't hold. Then you might have anyway a positive report from a reliable instrument with a tiny probability. Instead, you can have these probabilities higher for the positively biased instrument. For instance, I don't know, a pharmaceutical industry that wants to show that drug works tends to deliver reports about the drug, which tend to be positive more than if they would come from an unbiased source. Okay, so our results. So this is the model. So we have true positive rates. So false positive. So we have, these are the true positives, 1 minus epsilon for the reliable instrument. And this is the probability of true positives for the biased instrument, alpha, which is a little bit higher than for the reliable instrument. And these are the false positive results, I mean probabilities. Epsilon for the reliable instrument and gamma for the biased instrument. What happens is this. The wet phase, I mean, don't look at this, the wet phase for, in the case where gamma over alpha is lower than epsilon over 1 minus epsilon, which means that it fails when the rate of false to true positives for the positively biased instrument is lower than the false to true positives for the reliable instrument. What does this mean? It means that this instrument is more accurate, because even if it delivers false positives at a higher rate than the reliable instrument, still the ratio with respect to the true positives is lower than the ratio that the reliable instrument has. This means that the reliable instrument is non-biased but is more sloppy. And so the wet holds. Here we have gamma, here we have epsilon under this curve. Sorry, here. If we look at plausible values of gamma and epsilon, then in our case, the wet holds for most of the space, which means that we prefer replication from different instruments. So the bottom graph focuses on the area where both errors are less than 10%, both the, let's say, false positives of the biased instrument and the false positives of the reliable instruments. The wet phase in the narrow region between the diagonal here and epsilon, of course, where the diagonal is here, epsilon equals gamma, and the lower curve. So here, here we pictured alpha equals 1, but we have similar results for alpha lower than 1. We had to practically to analyze all the pictures because we don't have the analytical results, we have just the numerical results. So here is the third scenario. So we have a very similar picture if you can check. And I'm not indulging into the formalities. Here also the wet phase, but it's because these values are out of our models. Anyway, the wet holds for most of the space. So the wet tends to fail in our model with decreasing gamma and increasing alpha. So when the false positives of the biased instrument decreases, and when, of course, the true positives of the instrument increases. So decreasing for positive rate, increasing to positive rate for the biased instrument. And with increasing epsilon. So if the reliable instrument is more sloppy, then the bets tend to fail. Replication is favored when the biased instrument tends to be more precise with respect to the alternative one. Conclusions. So for very low values of gamma and epsilon, the instruments are believed to be precise if reliable, or with very low bias if they are biased. A testing for different instruments is more confirmatory, the area where the vet phase becomes negligible. When evidence is highly biased for the biased instrument, so gamma is much larger than epsilon, then hypothesis confirmation is greater from varied evidence. Here we have a high suspicion of positive results being false when coming from the same instrument. So a consistent series of positive reports is more confirmatory when coming from independent sources. That holds. And here is what fails. For high values of gamma and epsilon, both instruments tend to be sloppy and unreliable. The vet phase in this case, whenever the ratio of false to true positives is lower for the biased instrument, because two consistent reports from the same instrument increase the probability that they are true positives, via increasing the probability that they come from the more precise instrument, even if it is biased, between the two. But it's more precise. So this is also reflected in statistics, the bias variance trade-off. So beyond the mathematical results, the research leads us to be aware of analogies, and these analogies between natural epistemology, epistemology of knowledge acquisition in ordinary settings versus scientific settings or legal settings. So we provide a template on which to discuss different ways to conceptualize reliability and therefore different models of inference, how to model the diverse dimensions of noise, and what does independence of items of evidence mean, and so on and so forth. And in particular, of course, we have to discuss these assumptions, because if we model these inference through Bayes nets, then the relations between these epistemic entities are governed, are ruled by Markov condition, faithfulness, and sufficiency. Of course, these are assumptions which should be investigated, whether they hold in the different epistemic settings. So I'm done, but I want to invite you to possibly, if the COVID allows us, to a summer school and conference which should take place in Ancona in September 2021. It should have taken place in 2020. Unfortunately, it was cancelled because of the COVID. But since there is in September in Italy also the EPSA in Turin, and we are co-organizing with Jan Sprenger the EPSA in Turin. I mean he's organizing it, but I'm co-organizing a little bit. And I thought to organize it in September as well, so that people can go to Turin. Can come to the seaside and then go to Turin. And these are the lecturer and keynote speakers. Provisional, depending on whether it happens or not. Battigalli, who's a game theorist in Milan. Alfredo Di Tiglio, Phil David, Tina Eliassiviad, Brandon Patterson, Christian Henning, Clayton Vitteljohn, Sharon Rush, Eric Jan Wagemakers. I hope to invite other people in the future. And then there is, my postdocs asked me also to advertise this special issue for theory and decision, rationality and strategic interaction in the sciences. The call for a paper should appear soon, so keep track on that and join us if you like. Thank you again for your attention. Okay, now I stop sharing.
Thank you for that.
Oh, you're welcome.
Really interesting talk. As you formulate questions, please raise your hand in the participants bar and I will call on you. Or if you're Martin, raise your hand on screen because you're the host.
If there are none, I'm not offended.
Okay, I see a question from Micah. Micah, please.
Okay.
Yeah, thank you for your talk. This is my first exposure to bovins and Hartmann, but I thought a lot about reproducibility as a scientist. So I guess I want to first ask, you may have mentioned this, but your definition of an instrument, as in the scientific context, you see the same microscope not reproducing the same results from Boston to Japan. Well, it's not the instrument, it's the person operating the instrument. But, does that constitute an instrument in your definition as you think through these problems?
Yeah, I mean, this is in the paper that should appear, and then, I mean, it's the instrument. I mean, can be considered as a vector of different things, the data generating process, and the data generating process is not only nature, but also the instruments with which we detect nature, and the epistemic environment, which is the people that use the instrument, the reasons why they use these instruments, the assumptions that they make, and also the motives, included sponsorship or things like that. So, but I think that this is incorporated in the way we evaluate evidence. I think that when you read a paper as a scientist and you read these results, you analyze the reliability of the evidence depending on all these factors. The instrument that was used, the person that used it, the lab in which he works, the school he belongs to, and these things. And I think the instrument covers all these aspects, yes.
Okay, and irrespective of the reliability of the instrument, my thoughts were, same source and different source that you talked about. I'm wondering about your thoughts on number of sources. So now, given the condition, it is beneficial to get it from 2 different sources. Is it better to have 3, 4, and 5, 6 different sources? And where's the threshold in terms of how, is there dosage of reproducibility that changes your certainty?
Okay, I mean, ours are formal results. And so they rely on the assumptions. And the assumptions is, if you think that an instrument is unreliable with this probability and the false to positive rate, then depending on the number of sources, or reports, you might prefer to have the same source of different sources. But of course, this only relates to the pure epistemic aspect. Of course, in the sciences, you have also pragmatic aspects like financial costs and things like that, which should be taken into account as well. And in that sense, you will see, I mean, I was, for instance, talking about hydroxychloroquine, or keen, I don't know how you pronounce it. There is a heated debate on that. And of course, since there is no other alternative cure for the moment, I mean, there is heparin at a later stage, but as a preventative treatment, there might be hydroxychloroquine, just because the mechanisms tell you that it could work. But until now, all the observational studies told no, but they're still trying, because it's so important to, I mean, unless you find another treatment which is promising, at that point, okay, you throw away your hopes on HCQ, and then you go on for another treatment. But the stakes are so high that you still try like desperate until you find, or other treatments like, vaccines, but they are also not, and I also heard that even if you find vaccines, which is very difficult for this kind of retrovirus, still you should, since immunization with the COVID is not permanent, you should reiterate vaccination every 6 months, for instance. Is it feasible? I mean, also for other immune system? I don't know. So in view of that, you look for treatments for, therapeutic treatments or drugs that can, and so you repeat and repeat, or you look for different sorts of evidence, like animal studies, or you don't do exactly replications, like there are none of them are exact replications, because you test it in different populations with different background conditions, etc. But the more
sorry, yeah, it's interesting. So you bring up, at least in the COVID example, or you can even postulate certain cancer therapies that are seemingly more important. There's higher stakes. You're going to collect data of different sources. And it's interesting to me because it's not normal science in a Kuhnian sense, because the stakes are actually determine how much is being reproduced and determinant of reliability. And so sort of the thoughts I've had in terms of it's not puzzle solving for its sake, as I guess he put it.
Yeah, the point is, especially in medicine, scientists are much, I think, I have this sensing that scientists are much more aware of this decision theoretic background when they evaluate evidence, especially risk or environmentalist people. They reason the precautionary principle frame and so on and so forth. Instead, medical doctors, especially because they have so much information, they want to have dichotomous data, yes or no. So does it work? Doesn't work? Does it not work? And this makes it difficult to make them reason about evidence in the sense of seeing all the dimensions, not just whether it works or not, but see, okay, HCQ doesn't work, but isn't there anything else? Or for instance, now, of course, the risk profile of HCQ is much more unfavorable than at the beginning. Why? Because at the beginning, we didn't even know what it was. We thought it was interstitial pneumonia, but then we discovered it was not. So people were dying. They were all dying. And then the people that told me, but you know, as HCQ has possible cardiac effects. Okay, but they are dying. I mean, but now that they are not dying, of course, giving HCQ, which has possible cardiac effects, is not the same choice. So, and also, the point is also, I mean, they're all waiting for vaccines, okay, but their vaccines are still not there. So let's think about alternatives. And I have this intuition, I mean, the same intuition that what they call post-normal science, which is simply the consideration of the interaction of societal, economic, psychological, existential, anthropological aspects. For instance, now, I mean, we are all doing this conference online. We wear all masks and so on. What are the costs, the anthropological costs of all this for our civilization, for our work, for the configuration of our society in the long term? Can we bear them? Right.
Yeah, thank you. It's interesting. The puzzle solving is contingent on society.
Thank you for your questions.
Yeah. If you have other questions, please raise your hand. I see John Fuller.
Thanks so much, Barbara. I'm looking forward to seeing that BJPS paper when it comes out in the next 10 years, sometime in that time frame. So my question is actually just a simple one. So what do you think are the biggest upshots of your formal modeling analysis for the context in which you started? So pharmacovigilance, but also harm assessment more generally. If you had to meet again with these policymakers, what would you tell them based on the results of your modeling?
It was so fun. I mean, if Sana Yukola is here, maybe she knows. Is she still there? No, maybe not. Yes, she's here. She participated once in a meeting in Uppsala. And this was the hardest one. In Uppsala, I didn't have much success, notwithstanding the promises. I mean, in France, it was wonderful. In Germany also, very good. But I work mainly with France, Italy, and Austria. And I had to reframe all our, I mean, I couldn't speak when I speak with philosophers, of course. And the point was really to reframe and to my discourse, but I really learned a lot. Not only, I mean, from them, but also by reframing it. For instance, the most interesting thing was to say, okay, but what do we need this for? And so, and the main thing was really to represent your knowledge, to make transparent all the inferential paths that you're making, and then possibly, I mean, you can also not quantify it. I mean, it's not that we want to quantify. It's more that we want to make a template that they can use also for sensitivity analysis, for instance, and then see what dimensions of evidence are relevant in a specific case. If you say, and then you also see, what kind of evidence we would need and would make the difference if we had it for this assessment. The most difficult thing, however, is the fact that, especially at the beginning, they don't have many data. I mean, that's the reason why I developed the Bayesian framework, because at the beginning you don't have randomized control trials, of course, because you just have clinical cases, individual clinical cases, or basic science studies. The point is that at the beginning really is to put together the evidence and see whether for that patient the drug really caused the side effect. And so this is more in the legal framework. That's why my PhD student now is working in legal evidence. because this is more about counterfactuals and it's about framing the epistemic network in a specific way. I mean, you have to represent that case and then embed it in the general framework. Another thing which is interesting for them is that if you have a case series, you cannot do much with that. It's just that you have repeated cases of analogous patients having the drug effect, the IDR. But with that, in the difference-making node, you can embed them. It's not difference-making for a group, like in a randomized control trial, but it's difference-making for individuals that you put together. And so this can update the hypothesis of causation anyway. I mean, it's not, it has not the same strength of a randomized control trial, but it can be in some way put together. And the main thing was really exactly that in these settings you have fragile, heterogeneous, sporadic data, and they are happy at least to have a cognitive instrument to put order in this. And, I hope, I mean, these collaborations go on now with the agencies, although it takes a lot of time and energy, because they have their own hierarchy, their own processing of I mean, also just the work schedule, the daily work schedule, and so they cannot, you are at their disposal, they cannot be at your disposal, of course. Thank you, John.
Last chance for a quick question.
Martin?
Martin, I see you.
Yes, so I'm not sure if it's a quick question, so perhaps we can continue this chat either later on or at some other occasion. But so you mentioned that the sort of the formal abstract framework that you developed in your talk, you mentioned that now you are sort of applying it to cases, perhaps checking to what extent it is applicable and where it perhaps may also reach its limits. So I was wondering whether you could say briefly, something more about what particular cases you have in mind and any preliminary results.
Yeah, for one of the papers was on dose-response relationship. So what we are doing now is we focus on specific lines of evidence. We really address the framework piecemeal. So we start with the dose-response relationship because they say it's the most important one. It's the first you see, I mean, you look at. And so we have we had some paper, I mean, I had done a study on paracetamol and asthma in pediatrics, and there were those response evidence studies. And so we put them together and we have a paper on that shows how the probability of causation increases considerably considering this evidence. So we quantify it just by considering diverse possible curves of those response, and then through, let's say, updating through the likelihood of the course, given that there is those response, we update the probability of causation. And the paper is one of the papers I cited. Now with the Italian agency, we are working on the Natalizumab Pml Association, which is interesting because it's a drug that can cause, it has a very interesting mechanism, in the blood, but by the same mechanism it can cause, it's for multiple sclerosis. This is a drug for multiple sclerosis, so it is a very important drug, and they withdrew it and now they accepted it again, but it has a very oscillating risk-benefit profile because of these side effects on the cell. And now I don't remember very well the phenotypic effect. But the point is to see to what extent this is caused in different populations. So we look at, I don't know, pregnant women, we do subgroup analysis, always looking at the dose-response relationship. So where the dose-response relationship is stronger in which subgroup. So this is more about external validity in the sense of whether we should circumscribe the use of this drug in different subgroups. Another thing that we are planning to do is with the French drug agency, if I mean, we are applied for a project there, and it's that they make us available a big database on drug consumptions in France, and databases about side effects. And so this is something that Francesco will do, especially, is to compare and make those response, let's say, results, I mean, evidence for these, I mean, comparisons, consumptions, and then those response depending on the consumption. And of course, appearance of adverse drug reaction depending on the consumption. And this is also going in the direction of consolidating the dose response relationship. And but with the other drug agencies, we already studied, for instance, another, and this was the mechanism line of evidence, another drug side effect relationship, which was amoxicillin and DRESS, which is a complex syndrome. And this was interesting because we compared e-synthesis to ABM+. And we saw what happens if you use e-synthesis with respect to what happens if you use ABM+. Of course, there are two incommensurable things because we try to represent our inference patterns in probabilistic terms, in Bayesian terms. They are more qualitative, but it's interesting. It was interesting to see that the two came to relatively similar conclusions.
Wonderful. Thank you so much.
Oh, thanks to you.
Okay, let's thank Barbara. Thank you so much.
Thanks to
I
you.
hope to hear more about this during the break.